gases. Approximated, as always, we never quite get fully there, but we can get there if it's low density in particular. So again, empirical observations, most of you have seen this before, so I'm moving fairly quickly. First off, we're going to want to ask ourselves, what are the typical parameters that we might be able to measure macroscopically for gas volumes? Well, I think pretty obviously the things that we'll be looking at are three. The volume of a certain gas, its temperature, which is uniform, and the pressure it is exerting, if you will, or the pressure that it has, kind of the pressure that it's exerting. So we have three macroscopic variables. Pressure, volume, and temperature. Okay? Now, we've at least introduced all of these variables already. Pressure from last semester, force per unit area. When we discuss fluids, so we know what pressure is. Volume is pretty obvious. Temperature, we haven't talked about units yet. We're about to. So we have three macroscopic variables. And in the early history of studies of ideal gases, several behaviors, very simple behaviors, were uncovered about the relationships between these macroscopic quantities. I'm quickly going to write them up, and then we'll pull them together in the form of a single equation, so-called ideal gas equation. So, empirical observations. I'm just going to write these down sort of in terms of pairs. I'm not going to mention names or laws, so they do have names and laws associated with them. But it turns out that if you look at an ideal gas and change one of these parameters, keeping the others, at least keeping one as a constant, what you will find is the combination of P times V is a constant, assuming that T is fixed. Okay? So that's one set of observations. Again, this has a name and a law associated with it. I'm not going to bother you with that. So the combination of P times V is a constant if I keep T fixed. It turns out that the combination of P over T is a constant if I keep the volume fixed. And lastly, it turns out that V over T is a constant if I keep the pressure fixed. Okay? So you can see there are three sets of behaviors here. I take one variable, keep it constant, and look at how the other two respond to changes in each other, so to speak. And I get roughly these behaviors. Okay? So these are famous early experiments in so-called ideal gases. And what I can do, of course, now is combine all of this together in the form of sort of overriding equation. And roughly speaking, what we would expect is that P times V over T, sorry, it's not coming out so well with a new piece of chalk. But what you would expect is I can combine those three behaviors in a single descriptive equation. And there it is. So let's take a look at it. It's telling us that for these three macroscopic parameters, under the assumptions of this being a rather low density dilute gas, this combination of variables is always constant. So change one, how do the others respond? Pretty easy. So this is getting us already fairly close to a useful, workable, ideal gas equation, but the question is, what is the constant? So this is already of some significance, this behavior. What we need to make it actually workable and useful is to figure out what the constant is. So what is the constant? Here it's going to turn out to be useful for us to think about the basis on which we want to count how much gas we have. Okay? What do I mean by that? It's kind of a measure of how many atoms or molecules we have in our system. And you can imagine that these behaviors depend on how much gas we have. That seems pretty obvious. So what this needs to do is somehow be a measure reflect the amount of gas that we have. Okay, what do I really mean? The amount of gas, what I really mean is the number of atoms or molecules. Okay, so no big surprise that this behavior is going to depend on how much gas we actually have. So I need to be able to count how much I have. So we're going to start off by counting this in terms of number of fundamental constituents. And if we do this, let's call the number of constituents n, big N. So this means the number of atoms or molecules. What I can write is the following, that PV over T, well, it's a, I didn't explain this very well. It depends on the amount of things. So I need another constant. So let me call this other constant K, and then I need it to be proportional to the number of constituents. So I can write something that looks like this. Okay? So here's my number of atom or molecule constituents. Once I've got that, then I'm left with the need, it turns out, for some other constant. And this is what becomes known as the Boltzmann constant. Okay, let me write up its number, which I can't remember off the top of my head, but here it is. So this is 1.38 times 10 to the minus 23 joules per, okay, a little bit out of order here. I need to have a temperature unit already. So I'm introducing a temperature unit here. Let me just describe briefly what it is, and then we'll define it a little more carefully in a few minutes. Okay, so this is a number that somehow relates energy and temperature. It's sort of quite interesting. We know, with the benefit of hindsight, that energy and temperature are kind of related very much to each other. So this is something that's relating for us, energy and temperature. Obviously a small number, but keep in mind that in general for microscopic volumes of gas, we have very large numbers of molecules. So this is in general going to be a very large number. This is a very small number. And we end up with an equation here that's going to kind of work for all situations. So this is one way of defining the constant on the right-hand side of this relationship. Okay? So let me pause for a moment, just sort of give you a sense of what sort of things we might be doing. If we're given a volume of gas and we know how many fundamental constituents it contains, namely N, we've got now a newly defined constant. That means we can look at these three macroscopic parameters. We can tune them, change them as ever we wish, and we can easily figure out how the system responds. So that's fine. We've actually now already got the so-called ideal gas equation. And I'm going to write this as on a molecular counting basis, because it's dependent on the number of fundamental constituents, big N, that we have in our gas. Fine. We can easily do calculations in these units, but it turns out very often, for the reasons that I described, often our volumes of gas have very large numbers of constituents. It's nice sometimes to work with different unit systems. And instead of the number of constituents, I'm going to introduce the idea of moles of material. I imagine most of you have come across this, primarily in chemistry perhaps. And once we've done that, we can recast this not in terms of counting the number of molecules, but in terms of counting the number of moles. Okay? There's no new physics in this, it's just a different unit system, different system that may be more convenient for the numbers of interest. All right, so let me just write this up in the molar basis. But first off, we need to make sure you remember the definition of a mole. So, or in a molar counting basis, I'm going to pause and ask you guys to tell me if you remember the definition of a mole of material. Let's get some new volunteers. Way up in the back, Sophia.
6.02 times 10 to the 23rd.
Okay. Yeah, sure, fine. Its definition is like many things in fundamental science, kind of annoying, but so 1 mole is defined, that's what the triple equality means here, to be the number of constituents in 12.0 grams of carbon-12. Okay? But yes, in fact, it is Avogadro's number, which is, what was it, 6.0 times 10 to the 23?
028.
Wow. Wow. They almost raised the stakes.
I like 8.
Something like that?
Yeah.
Yeah? Okay. It's a big number, right? Okay, let's not get hung up on this. It's simply a change of unit that allows us to define big numbers in terms of small numbers. Okay? So 1 mole is now 6 times 10 to the 23 fundamental constituents. So if we take this definition, we can recast our molecular ideal gas law in terms of number of moles. So let's see, number of moles, little n, is number of fundamental constituents divided by Avogadro's number. So that's how we would determine the number of moles in some particular setting. And we can then also see if we can make our lives a little bit simpler in terms of figuring out molar masses. So here's a molar mass of carbon-12. We can also write that this is the mass of the sample we're interested in divided by the molar mass. Okay? So all right. So now what I'm going to do is take this and recast it not in molecular counting basis, but put it over in molar counting basis. So what I have now is the following. So I've got PV over T initially in my molecular counting basis. Now I'm going to write this as NA, let's see, times N times AB. Let me make sure I've got this right. So I'm now writing N in terms of the number of moles and the Avogadro's number, so N in terms of number of moles and Avogadro's number. And now what I'm going to do is take this combination of two numbers, Avogadro's number and Boltzmann constant, and I'm going to give it a new symbol, a new name. I'm going to call this R, which is the ideal gas constant. And for completeness, this is 8.31 joules per mole Kelvin. Okay? So what I'm doing here is changing units, changing counting from molecular basis to molar basis. And what this will tell you now is that I can write that this is N times R. Okay, so not a great use of chalkboard real estate on my part, so I'm just going to highlight this again, draw out the key features. So now we've got the ideal gas equation in molar counting terms. It's PV over T equal to NR, or in the form that you're perhaps more used to seeing it and more used to remembering it even, PV equals N times R times T. Okay? So there we are. Or if you like, over here, PV equals big N times Boltzmann constant times T. For us, we're going to usually use this form. It's generally much easier to count in terms of moles rather than molecules, just because of the orders of magnitude involved. We're going to make use of this ideal gas equation quite a bit in the next couple of minutes. Okay? Let me just pause and ask more questions on this sort of fairly simple introduction of the ideal gas equation. Yeah.
What's the definition of Boltzmann's constant? Like, where did that come from?
It's a good question. I actually don't know where it was first introduced. It might be here.
Okay.
But I don't know. I'll find out. That's an interesting question. It appears many places in thermodynamics and in more sort of recent, more advanced thermodynamics. If you think about the history of this subject, this stuff came very early on. And it may well be that this is where the constant was first introduced into the mind. Don't know. Good question.
Okay.
Other questions about the ideal gas equation? Yeah.
Are there specific units tied to each
Yes.
right there?
So I've gone about this in a little bit of a backwards way. So now we're going to explore that because it's important. So first off, I've sort of, in a rather sly way, already introduced a temperature unit, Kelvin. Okay. So now we need to take a little bit of a sidetrack and make sure we know what this is and define it carefully. Before we define it, let me basically tell you that it is an absolute temperature scale. And in particular, it has a 0 point, which we're about to talk about, which is, it turns out, at the bottom of all possible temperature scales. That turns out to be a very important statement. And so in that sense, it's an absolute temperature scale. It has a 0 that truly is the physical 0 of possible temperatures. So that's important. And so in this sense, T must be in this Kelvin unit of temperature. So the absolute temperature. That's one thing that's necessary. Volume, well, volume is just volume. There's not much to say about this. Pressure, though we didn't dwell on this much in the first semester, it's important for me to point out that this also better be an absolute pressure. So this needs to be, again, I apologize for my lousy use of real estate on the chalkboard. We will hopefully figure out a better way to do this if we get going into this room. So this means I need to worry about pressure on an absolute scale that again has a physical 0 at the lowest possible physical pressure, which is to say 0. That may sound obvious. We pretty much only talked about absolute pressure in the first semester, but you will remember along the way, though we didn't talk about it much, there was the introduction of the concept of a gauge pressure when we talked about fluids. So that's basically a pressure with an offset or a pressure with respect to some different 0 definition. So what you're seeing here is that everything needs to be in absolute scales that have physically correct 0 points at the actual physical minima of the various quantities. So that's going to be important when you apply the ideal gas law, that you are always working with these absolute units. So pressure should be the absolute pressure in pascals, volume, the volume in liters, I guess, meters cubed, and temperature in Kelvin. Okay, so we'll get a little bit of practice in working with units, not today, but as we go into next week. So thank you for raising the flag about units. Let's, in a moment, move on to talk about temperature units. But before I do that, any other questions on the ideal gas equation? Yeah.
Just to clarify, so absolute means like it's just always positive, right? Or
Correct.
okay.
Yeah. It's a nice way of defining it. Yeah. Okay, so temperature scales. 3 in common usage. For us, we're going to tend to focus on the absolute temperature scale of Kelvin, just to make sure we know how to transform between different units. So you're all, I think, very familiar with the so-called Fahrenheit temperature scale, somewhat less so in the US with the Celsius or centigrade scale, perhaps even less so with the Kelvin scale. So temperature scales and units. So let me do this in no particular order, except maybe based on familiarity. Fahrenheit symbol F. This is what here in the US we tend to use most commonly. So this is a scale that has the following kind of definitions. There's interesting history behind all of these, which you can read about if you're interested. But the definition is, I believe, roughly as follows. So 32 degrees Fahrenheit and then 212 degrees Fahrenheit, defined as the freezing temperature of pure water at standard atmospheric pressure. You don't have to worry about any of this stuff, but I'm just throwing it in for completeness. And as you hopefully know, the 212 is defined as the boiling point of pure water at standard atmospheric pressure. Okay? This has some very interesting history that doesn't have exactly this origin, but I'm not going to talk about it. So this is roughly the Fahrenheit scale. Celsius or centigrade. As with many aspects of a metric system, it tends to try and rationalize things somewhat in terms of decimal systems. So in this case, we are defining the 0 point of the Celsius scale to be the freezing point of pure water at standard atmospheric pressure, which I'm not going to write. It's a waste of time. And then 100 Celsius again is associated with the boiling point of pure water at standard atmospheric pressure. Okay? So those are two definitions of the Fahrenheit and Celsius scale. You can easily do a conversion between them based on those informations. And what you will find, just so you know, is that, for example, I can write a conversion between temperatures in Fahrenheit versus temperatures in Celsius that looks like this. Okay? So again, I don't care much at all about any of this stuff. You may once in a while have to do a temperature conversion. It's all definitions, no interesting physics really. So let's just move right along and talk instead about the Kelvin scale, which is physically the most interesting and most useful of the scales that we're going to use. First off, it's absolute in the sense that it has a 0 point at the lowest possible temperature, or in the way that you described it, temperatures are always positive on the Kelvin scale, which is obviously not true in these scales. So let's go back and see what we can learn about the Kelvin scale, how it's defined, and then a conversion scheme, which maybe we will use once in a while if you're given temperatures in either Fahrenheit or Celsius and we want to convert them to Kelvin. Obviously you need that. So why did I talk about ideal gases before introducing temperature scales? Well, now is the answer to that, because it turns out the Kelvin scale is very much defined in terms of behaviors of ideal gases. Okay? So let's revisit our ideal gases. And you saw some simple relationships that characterized the macroscopic dependence of the parameters of an ideal gas in terms of those sort of constituents of the ideal gas law. What it turns out we can learn from this, you already know it, because we've already described it in terms of one of those constituent equations, is the following. Maybe I take some volume of some ideal gas and I map out pressure versus temperature dependence over some range of temperature. So let's say I've got a gas 1 in green, and I'm measuring, let's say, even on a Celsius scale, so it is 0. I'm measuring the volume of gas and seeing how its pressure varies with temperature. Well, first off, let me write this now in terms of the molar form of the ideal gas equation. Pressure is proportional to temperature, linear proportionality, at least a good approximation. So we expect a straight line. Maybe I measure over this range and I do indeed get a straight line. Fine. Now I'm going to take a second gas, maybe different type of gas, its volume, whatever. We do this, gas 2, and again, it's a gas quite dilute, it's roughly following the ideal gas behavior. I again get a linear behavior, maybe a different slope if it's a different gas. Okay? I didn't mention that explicitly, but in general you're going to have different maybe behaviors here, at least in the case that there may be deviations from ideal behavior. So depending on how much gas I have, I may get a different slope here. All right, so the question is, these suggest something interesting if I'm to extrapolate down to very low temperature. And maybe I can't do this physically, both for technical reasons, but for more important physical reasons. But I can imagine that this ideal gas linear behavior tracks all the way back down to here. Okay, I'm going to have to redraw one of my lines because I drew it very poorly. Let's say the slope on this one's a little different. And I can do the same thing with this gas. So I can extrapolate back down to here. And it turns out if I do this, all of these lines that I extrapolate based on the ideal gas behavior at high temperature converge at a common point. Right? So they converge here. Now, I said maybe I can't do this in practice for both technical and physical reasons. Practical reasons, I think, are reasonably familiar to many of you. It's kind of hard to build refrigerators, which is what we would need, to cool down volumes of things to increasingly low temperatures. These days our technology is pretty good, and in fact we can get very close to this, but certainly historically it was pretty hard to get down to these very low temperatures. So now we have the technology to do it. Well, what's the physical reason that things may not work here? Well, we haven't talked about it too much yet, but you already know that if I take most, maybe even all under the right parameters, most volumes of gas and cool them down, they're not going to remain gases forever. At some point, they're likely to liquefy, and eventually they're going to solidify. So this is not something that we will observe in general in practice. There are some rather exotic materials where we can get very close to this, but in no case do we expect to actually be able to keep the gas and gas phase down to this very low temperature. So it's an extrapolation based on the ideal gas behavior. What it's suggesting is that there is a physically absolute minimum temperature that nature allows, and this is the so-called absolute zero of the temperature scale. So this is indeed converging at absolute zero. Now, I started drawing this on a Celsius scale, just to give it sort of some sort of contact with day-to-day temperatures. On this Celsius scale, this number down here is approximately minus 273 degrees Celsius. It's not exactly that, but it's close. So that turns out to be the temperature extrapolated from this behavior that we believe to be an absolute zero. And this point turns out to be the sort of reference point for our Kelvin scale of temperature. And so the number precisely is, well, somewhat more precisely, minus 273.15 degrees Celsius. So we're going to make use of this now as having defined for us an absolute temperature scale. And we're going to set this to be the 0 point of that absolute temperature scale. So we're going to define this as 0 Kelvin. Kelvin is one of the important scientists involved in early thermodynamics. Okay, so now we've got a 0 point. What about the size of the units? It turns out the definition of the size of the units is exactly the same as the unit size for the Celsius. So 1 degree Celsius in terms of units is exactly the same as 1 Kelvin. It's just that the 0 points are offset. So now we've basically defined a new and more useful, physically useful temperature scale, namely the Kelvin. So, again, taking these pieces of information, I can easily get a conversion factor, and I'm going to do it in this case for conversion between Kelvin and Celsius for what I hope are obvious reasons. Now I have the temperature in Kelvin is whatever we measure in Celsius plus this constant offset of 273.15. So, room temperature, often taken to be, this is kind of quite a warm room, but rounded, we often talk about room temperature being around 27 Celsius. That doesn't sound rounded at all, but if you take 27 Celsius and convert it into Kelvin, it's roughly 300